Hello everybody, welcome to the first lecture in the course of Construction of Electronic Systems, and the lecture will be about the printed circuit board basics and materials. A printed circuit board is a board that has three main properties. These are electrical properties, mechanical and thermal properties. The components that are soldered on the printed circuit board of course have to be connected electrically, but the board also provides mechanical support, and it conducts heat away from the component, so it has also thermal properties. For printed circuit board, we usually use the abbreviation PCB, but sometimes you also see printed wiring board term in literature, so PWB. And why should we care about the printed circuit board materials? Well, in the design phase of the printed circuit board, every electrical engineer should be aware of what kind of materials are available, and according to that, the design rules are then made and applied to different types of PCBs. And of course, you should be aware that the different properties of the PCB also means different price ranges, and usually you should construct a PCB with the lowest price point possible, and therefore you have to be aware of the limitations you are then seeing, and the design should be then tailored to these limitations in order to make a working electronic prototype, and also then later that this prototype will be manufactured according to the rules, and of course later that the electronics will work as expected during the whole lifetime reliably. So all that is important, and every electronic designer should be aware of what types of materials should or he can choose from, and what are their electric properties. There are a few features on the printed circuit board that everyone should be aware of. So printed circuit board can have different layers, not only 1, 2, even more. I mean 4, 6, 8 is not exceptional nowadays. So he should be aware of the dimensions of the holes, of the thickness of the layer, and then the dimensions of the lines, the clearance between lines, and so on. All that is dependent on the type of the materials that are chosen for a specific application. Let us continue. Well, usually what we distinguish here in the printed circuit board technology are two main technologies. One is called through-hole technology, THT, and the other is surface-mounted technology, SMT. As you see here, the through-hole technology uses components that have leads that are inserted in the prepared vias, holes, and these components are then soldered on both sides. So it's mechanically more stable, but on the other side you have large components, the density is very low, so usually these technology is used for the highest reliability board on one side, but on the other side the cheapest and the lowest complexity boards. On the other side, we have surface-mounted technology, which took place in 80s, and then more or less most of the high-end electronics is made of this technology, and you have the surface-mounted components that are soldered on a single side. You can then have double-sided placement and so on, but these are details. Before the printed circuit board was invented, the components were soldered more or less in the air and connected with wires, and it was a really painful job, and higher quantity apparatus were not well, were able to be produced, but not really efficiently. And the inventor of the printed circuit board is this guy here, who actually made a prototype of the etching process of the foil that is attached to some sort of a isolated surface. So this is the patent. The patent is on the actual transformation from the schematics to the placement of components, connecting the components, and finally making these conductive surfaces that are connecting the components together. All that was patented, and it was patent was granted, I think, or applied at least, in 1944. Okay, let's continue. First PCBs were like that, more or less single-sided printed circuit boards that had components on one side and the tracks on the other side. The components were tracked from this side, were soldered from this side. So the top side was also called component side because the components were on that side, and the other was called solder side because the soldering was made on that bottom side. Still now, some of the quite used software still uses these names for the layers. So that's for the component side for the top layer, and solder side for the bottom. So these first single layer PCBs were then, as I said, made with one bottom layer with the copper and top layer with components. They were single-sided and the through-hole components were used. Of course, in 70s and more later, the density of the PCBs increased, so they introduced double-sided PCBs, where the main difference or the main technology, the key technology invented here was the through-hole plating, so that the holes were conductive, and by that you could connect top and bottom layers together to form so-called via. A via is a connection between top and bottom layer by means of plated hole. And also in that area, in that time, the surface-mounted components were also introduced. Later, of course, the density of PCBs increased, so the multi-layer printed circuit boards were introduced, where not only the top and bottom layer are, also the mid layers are now able to be made. And of course, still the main key technology is the plating of the holes. And so we can have now up to, I would say, more than 20 layers. 12 layers is nothing really special now. And by that you can make really high density PCBs. So the printed circuit board can be classified on different, criterions. So you can say, okay, we can have digital, analog, mixed signal circuits, radio frequency or microwave, and according to that type you have to choose the right materials. You can have through-hole components, surface mounted or mixed. Then you have also ball grid array components, which cannot be like made or placed on every type of material. You have one-sided placement, double-sided placement of components. You can have also embedded components, which are embedded inside the layer. So you can have all these combinations. The main material can be, of course, rigid, it can be flexible, it can be combination, rigid, flexible. You can have one-sided, double-sided, multi-layer PCBs, so several layers of copper and so on. Of course, you can ask yourself whether you want high reliability or high power electronics or extremely low weight electronics, and that also depends on the material and the complexity. What is the number of layers? Is the problem of electromagnetic compatibility? Should it be lowered? What is the density of the tracks? Whether the very small wires, micro wires, so-called micro wires are used, are wires also buried, and so on. All that then depends on all these criterions, depends what kind of material you will take for the printed circuit board. Okay, let's go to the materials. What are the core materials for the printed circuit boards? Well, usually what we divide the PCB is to three main materials. The core material, which is also called laminate, the copper layers, which are conducting and of course are forming the tracks, and the surface finish on top and bottom. So these are three main materials that everyone should be aware of, and you can choose of different quality and types of these materials. So let's go first to the core laminate. And for the core laminate, what is usually used is some sort of insulator. So we are talking about dielectric materials. And these dielectric materials have to be reinforced, because the dielectric material itself can be very fragile. It could break easily, so it has to be reinforced by some kind of fabric. So this combination of dielectric and the fabric we call with a common name, which is called prepreg. So I'll just go to the next slide and then I will come back. So the prepreg is a pre-impregnated reinforced material. So that's where the name comes from. So it is a combination of some sort of a resin and the glass fiber. And these two materials together then form a sheet, like a very thin sheet, that is then rolled into rolls and can be used to make PCBs at the end. Okay, so as I said, the prepreg is made from epoxy resin and fabric of some kind, let's say glass fabric most usually. What are the other materials you can use? Well, these epoxy resins can be replaced by formaldehyde, which is not commonly used now, but it was really common in, let's say, old times, let's say 20, 30 years ago, because it's quite environmentally unfriendly. So epoxy is now mostly used, and it can be combined with two types of fibers, either glass fabric fibers or paper fibers. Glass fabric, of course, is more quality material than paper. But you can have other dielectric materials as well, and they are divided into groups. First is thermosetting resins, and the second is thermoplastics. Among those, the most important are polyamide, and polycarbonate and polyethylene terephthalate. Polyamide is also called Kapton. And polycarbonate and polyethylene terephthalate is the common plastic we used every day for bottles. So there are also some other materials that are quite often used in the group of special laminates. And these are metal laminates, which are used usually for high power application, where the heating is very important, or the heat dissipation is very strong. The other is polytetrafluoroethylene, also called Teflon. As you might remember from every kitchen, we have Teflon layers on our dish for cooking. And this is used for high frequency applications and low weight. I'm not sure what are these liquid crystal polymers. I just found out that they can be used and they are used, but I'm not sure what is the, I would say, the application. and ceramics. Ceramics is a really special material for high-end electronics, for really, let's say, either high power or high frequency applications that usually I wouldn't say it's commonly used in everyday electronics. So among those, what is now quite important and what you should remember as well is metal laminates, and also PTFE. Okay. So let's go further now. What are the properties of this core laminate material that we should care about? Electrical characteristics. Well, the permittivity or dielectric constant is the first one. That's important because the speed of propagation of electric signals is dependent on it. It's quite easy to say, let's say here, I will try to write an equation, that the velocity of the signal on a PCB is equal to the c, that is the speed of light, let's say c0, divided by square root of the permeability, relative permeability, times the dielectric constant or permittivity. Since the relative permeability is, let's say, almost, let's say it's 1 in these dielectric materials, the permittivity is the important factor. And that one should be as low as possible to achieve higher propagation speeds for electrical signals. And that therefore this is an important property. The other is insulation resistivity, of course. What we want is highest resistivity material possible. The third is dissipation factor. Why is dissipation factor important? A dissipation factor is actually a factor that tells you how what is the decrease of the amplitude of the signal at a certain length that is traveling. So it's similar to the I would say the losses, the electromagnetic losses in material. So for high frequency application, a dissipation factor is important property. And the dielectric strength in volts per meter, it tells you at which electric field the electric breakdown will happen. Among these, I would say the first property everyone looks at is permittivity, the most important property one. Then you have thermal properties like glass transition temperature. A glass transition temperature is actually the temperature at which let me just wait a little bit, at which the epoxy resin or the dielectric resin would start to leak. It would start to lose the property of a glass. That's why it's called glass transition. It turns to be soft and it will start to leak out. The glass transition temperature is usually denoted as Tg, and Tg goes from 100 degrees up to 100 and maybe 30, 140, 150. It's not the temperature where the material would just burn. It's a temperature when it becomes soft, and keeping the PCB long enough at this temperature would then cause deformation and leakage of the resin. Thermal expansions are of course important for reliability issues and the thermal conductivity for component cooling. These two here. Then what you should also be careful is the permeability of water. How permeable it is for water. Usually the moisture should not enter the laminate, because then it would decrease the dielectric strength and increase dissipation factor and decrease insulation resistivity. So they should be water repelling. They of course, the chemical resistivity is also important because of the etching that happens. That is one of the procedures during the PCB manufacturing. And cost, of course, the cheapest the better, as usually. All right, so these are all properties that one should care about. Which of these are really important for everyday electrical engineer? I would say the most important is permittivity. Then the thermal conductivity. These two, and then maybe the glass transition temperature for high power electronics. These are the most important ones. All the rest, more or less, are there in the safe range, I would say. Okay, I forgot the cost, but yeah, that's obvious, isn't it? All right, let's go into the materials a little bit more in detail. Here I'm listing the basic pre-preg core laminate materials that let me remind you that a pre-preg is a pre-impregnated cloth made of epoxy resin or a resin, as it is, with some reinforcement, either paper or glass fiber. All right. We have two main groups of materials for that. First is called FR, which means flame resistant or fire retardant. The basic property is it should not burn with flame. And the other is CEM or composite epoxy material. Okay, the FR materials go from FR1 to FR4 and CM goes from CM1 to 5. They are a little bit different, but among those, I would say the most used nowadays are FR1, FR4, and CM1 and CM2. Okay, so among those, the FR4 is far the most common ever. So 90% of PCBs are made for FR4 because it's the most, I would say, has the best price performance. But for, let's say, the lowest quality and the lowest complexity electronics, we also use FR1 and these two. So let's go a little bit more into detail for each of these materials, starting with FR1. The FR1 or even FR2 are very similar. The code name is Pertinax, which is actually a trademark name. The material is paper and phenol formaldehyde. This is what I tell you also that it's quite, I would say, now obsolete. But we can still find these PCBs. How do we distinguish them? They are more or less brown, opaque. They are one-sided, so tracks on one side, components on the other. Low-end consumer electronics, high volumes, low price, low frequency. All these properties here would tell you that they are not intended for high frequencies and also for high temperatures. And that's an example of such a circuit. I can also show you live if you want. Okay, here, see, this is an electrical circuit made of FR1. So the green color on bottom shouldn't confuse you. It's the protective layer made of some protecting coating. Otherwise, the color of the FR1 is more or less yellowish brown, and you can see that it also has it's a single-sided low priced PCB without any big high density electronics on it, just through hole components more or less. And you now see such material in power supplies for laptops or for computers and for other devices more or less. even in some audio, low-end audio electronics. Yeah. Continuing here, a single-sided FR1 from the sides would look like that. If you cut it, you can see this is a through-hole component, and then you see here the paper layers and the copper on bottom here. Continuing with FR4. FR4 is the most commonly used material now because it more or less has all the properties needed for everyday electronics. It's made of 8 layers of glass fiber, and it's reinforced with epoxy resin. It's semi-transparent, so you can see here that you can actually see through it. If I put my hand here, you see the shadow of my hand, so you can see actually through the PCB quite easily. I can also shine some light through it, and you will see you have maybe, yeah, you see the both layers. So because it's made of glass fiber and epoxy resin, it's actually semi-transparent, which is quite good, isn't it? About the color, let me tell you about the color. The green color, again, is just the color of protective coating. So you can have green PCBs, you can have red ones, you can have, watch out, purple ones, you can have black, and my favorite color, you can have blue PCBs. Now, going back to what we started with, it is intended for general electronics. It has relative permittivity around between 4 and 5, I would say. That's important parameter. Dissipation factors are quite low, so you can make also high frequency electronics up to a few gigahertz. And the maximum temperature here is around 120, but you can get also 130, 140. It all depends on the materials, details, and of course the price. It doesn't burn with flame, it just smokes a little bit, and it smells as well. So that's the typical FR4 PCB. You can see that it has SMTs, it has quite high density components it can have, and therefore, yeah, that's usually the FR4. And this is the side view, cross cut, and you see these glass fibers that are waving through the material here. So because it's a cloth, it's actually interleaved like that. Yeah. So you have glass fibers here horizontally, and then you have glass fiber going through the material, and that's why it's wavy. And this can cause a problem. Let's go a little bit into detail here. The dielectric constant, or the so-called permittivity, electrical permittivity, well, it's not constant. I said it's between 4 and 5, but it depends on the content, resin content. What is the percentage of the epoxy resin with respect to the glass fiber, and of course the frequency. So telling you that that permittivity is between 4 and 5 is just I'm sorry for that, is just some, I would say, approximation. And let's continue. And not only it's not just the problem of the material composition, it's also spatially different. So you see here that if your track is over the glass fiber, or it is next to the glass fiber, it's different. So here is the glass fiber here, and then if the track is just next, if the track is just here, it will have more epoxy resin than here. So the dielectric constant also changes spatially because of the wavy nature of the glass fiber. Maybe in some cases that's not relevant, but at, let's say, in high frequency application, that's quite important. Here as well, the dielectric constant changes from the, I would say, from series to series, from batch to batch, which means that you have some tolerances from production, let's say at day one, and at day, I don't know, after 1 month, you would have different content of the material and therefore different properties. So that's also important. And why I'm telling you all that? Well, I'm telling you that because if you want to control your dielectric constant, which in some cases you have to, because you want to keep the property of the electrical connections really, how would I say, strict, then you have to care about all of that. So you have to order type of material that would exactly fit a certain dielectric constant. And therefore, your production manufacturer would have to, calibrate all these properties to assure you correct operation of your PCB. So knowing this is just, I'm showing you that just to make sure that you know that these parameters change, and if you want to have them really, I would say, constant or to be well defined, a manufacturer would have to try much harder and calibrate each series of the production to a constant or to a defined dielectric constant. And that's a problem because, let's say, I must tell you a story here that, let's say you make devices or electronics that has high frequency antenna, let's say 2.4 gigahertz, it's quite commonly used. And this antenna is made on a PCB. If you want effective communication, you have to tune that antenna to be directly, have the resonant frequency directly at the frequency at which this communication operates. Let's say exactly 2.4 gigahertz. This depends on the dielectric constant of material, the permittivity factor epsilon. And your design is then made for a certain dielectric constant, and if it changes because of that and those, your antenna would go off, and this would cause problems. So it's not something that I'm just making up because I want to be smart or something. It's actually something you should be really concerned about. Okay. The dissipation factor is another parameter which is also important if you want to make high frequency electronics. And for example, here you see different materials you can choose for. They are all similar to FR4 except maybe Teflon and these Rogers here, but more or less you see what is the loss of signal per 1 inch of the length of the line, and their differences are also quite important. If you want to go to high frequencies, now the 5G would go to 60 gigahertz, if I'm correct, at in a certain time in applications, and the materials are really important in that range. We'll talk about it sometimes during these lectures as well. There also temperature and humidity changes the dielectric constant and the dissipation factor as well. So to make sure nothing is constant, and all of that should be taken into account. If it's important, then you should choose the right material to be as stable as your application requires. Okay, here is a picture of an 8-layer FR4 PCB. So you see the top layer, 1, 2. So here maybe I can show with a laser pointer. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. This is a cross section, and what you should be careful about, or you should know that these structures don't have equal distances of the insulation layer of the laminate. You see here these lines are much closer together, and here is the higher distance. So you should be aware that from the manufacturer you can choose different stacks with different layer thicknesses and different arrangement of the stacks. So not all, let's say, 8-layer PCBs have the same structure inside. All right, let's go now to the composite epoxy materials. Usually CEM1 and CEM2 are the most used. Here I show you CEM2. They are also could be white, could be yellow, so you cannot tell from the picture itself what is the color or what's the material. But more or less, most of the data are similar to FR1, except it has 2 layers of glass fiber for better strength, and it's made of epoxy resin, not from formaldehyde. They are still made for low frequency applications, one-sided single layer PCBs for low-end consumer electronics. That's the picture of the cross section. You see the glass fiber layer on top, glass fiber on bottom, paper in between, and top layer of copper. All right, let's go to the metal-based laminates. Metal-based laminates are used for high power electronics where the heat dissipation is very important. Here these high power applications are, let's say, for example, LED light sources where LEDs have to be cooled down efficiently, then high power drivers for motors or high power converters, and all the electronics that now has to be really small, packed in a small package, and of course it requires quite a lot of cooling. And there you can choose between 2 groups of materials. One is based on aluminum and the other is based on copper. The copper is of course expensive, but it has better thermal conductivity. But there is a dilemma here. You know, I told you before that the base core material should be an isolator, but here the metal laminate is actually a good conductor. Usually it's a good combination, or let's say a connection between electrical and thermal conductivity. So usually good electrical conductors are also good thermal conductors, and vice versa. Good isolators are also bad thermal conductors. So in this case, what we have, we do not have whole merely metal substrate. We also have a very thin insulator, and this thin insulator here is actually electrical insulator, and there is a copper layer on top. You can have several layers, not just one. Usually in the basic applications there is one. There are 2 main groups of these materials regarding this insulation. First is direct bonded copper, where the copper is used to, it has ceramics as an insulation layer here, and the other is insulated metal substrate, or IMS, where the insulator is actually the epoxy resin as in normal FR4. These are expensive and has better thermal properties because the ceramics does not melt at 120 degrees, while epoxy resin would start to leak at that temperatures. But these are cheaper, of course. So the cheapest would be the copper IMS with aluminum base. And expensive would be, of course, the direct bonded copper, but it would work at higher temperatures. The basic property of these materials is so-called thermal conductivity, which is expressed as, let me show here, in watts per meter Kelvin, which would tell you how many watts of thermal flux or heat flux would run through the PCB vertically. Yeah, if you have 1 Kelvin difference of temperature, 1 Kelvin gradient at a square meter and 1 meter thickness. So you can also have a square millimeter and 1 millimeter thickness. That would be also the same. So this is how the direct bonded copper looks like. Copper laminate, thin ceramic insulator, and top layer for connections. The next material is Teflon-based laminate, PTFE, polytetrafluoroethylene. And this laminate is intended for highest frequency applications. It has the lowest permittivity between these materials, and it also very low density. So for very low applications such as satellites, airplanes, and similar. How you recognize it? Well, it's light or dark gray colored, and it has usually the microwave circuits that are made on it are shaped quite strange, not looking like normal circuits we are used every day, because these features, the geometry is very important, because the microwave frequencies are already, or wavelengths are already comparable with these features here. So this type of the shape here could already be a coil, or it could be a capacitor, depends on the length with respect to wavelength of the signal. So more or less you can recognize these high frequency or microwave circuits with this kind of strange features, which are not, I would say, for electrical engineer used every day, probably not very common. Let's go now for the flexible PCBs. Now, flexible printed circuit boards are made usually from plastics. So plastic materials that are commonly used are polyethylene, polycarbonate, and polyimide. Well, polyimide probably, or something similar, it's also called Kapton. So the Kapton is a trademark name for polyimide. Yeah. And it's yellow colored. So these are all made of Kapton. All these here. These are all made of Kapton because they are yellow, and you can easily recognize the Kapton being yellow. And it can withstand the highest temperature. Such a temperature that you can actually solder on them and they will not melt. So the Kapton plastics is the best plastics for soldering directly on it. And they are most used for electronics, portable electronics, where the space is of essential concern, and also cabling and flexible connections are there. This is an example of a keyboard, some cables, and some electronics cables with some extra components placed on it. This is also an example of such a electrical circuit that has some space constraints, and they made such a PCB directly to be part of the housings, or to be, let's say, adjusted to the shape of the case. The flexible electronics is gaining a lot of interest lately, and one of the applications that you can also have is a so-called combination rigid flex PCBs. So you have a classical FR4 which has an inner core layer made of plastics, usually Kapton in this case, and then it extends to the other PCB as here. What are the main properties, or what are the main advantages of this? Well, the main advantage is that it actually, you can access everywhere on this PCB. You can access the middle layer with a wire, and then you access actually the tracks on that flexible PCB. So you can make a connection between two PCBs from anywhere here to anywhere here without a connector. Absence of connector makes the board more reliable and therefore also cheaper on the other side. Enough about the core laminates. Let's go into the other layers that are also part of the PCB. And the next layer is a copper layer. A copper layer, you can have, of course, top and bottom layers, but also mid layers in between. But let's talk about the basics, top and bottom layer of copper. Well, you have two options. Either the copper can be electrodeposited, or it can be rolled annealed. So what's the difference? Electrodeposition is made electrically in a solution of some copper electrolytics, and you can make the thinnest layers with that. The rolled annealed copper from the other side is a foil that is then stick to the surface. It is much more smoother, and it has you can make thicker layers. So a PCB is usually a combination of actually both, because some of the copper is electrodeposited and the base copper comes from the foil that is stick to the surface. What are the thickness of the copper? Well, this is quite strange, because the thing is that the thickness of the copper comes from the USA imperial units. So the base is 1 ounce of copper per 1 square foot. What does that mean? 1 ounce of copper is a weight of the copper that you pour on a square shaped area of 1 square foot. And if you pour that 1 ounce of copper on that layer, it will have thickness of 35 microns. And that's the base. So you can either have 1/4, 1/2, 1, 2, 3, 4, and so forth ounces of copper, which relate to these thicknesses here. The most common is 35 microns for outer layers and 17 microns for inner layers. That's the default thickness of copper. On the other side, you have different thickness of core laminates, where the 1.6 millimeter is the most common one. That's the default thickness of any PCB, more or less. So if I show you here, all of these PCBs I have here, just to show you, they are all 1.6 millimeters. And this is also the cheapest PCB you get in a production. If you choose another thickness, it would be probably a little bit more expensive. And the price goes up if you go to a much thicker PCBs, let's say these here for mechanical strength, or if you want very thin PCBs on the other side, where they also become flexible and they are harder to manufacture and harder to handle. About copper, there is another interesting feature which we didn't speak about yet. It's the skin depth. The thing is that at high frequencies, the current tends to flow only on the surface. That can be shown actually here, if I can do it. So you have a surface, you have a conductor, and you have a ground here. And in between there is a so here I have a signal, and here is the ground, right? And here the current flows there, and then it returns on the ground. So the current would flow just here at the surface of the conductor. I'm not talking about DC current, I'm talking about high frequency current. And then it would go somewhere to some resistor or something, I don't know. Then it will return back on the upper surface of the bottom ground. So the current tends to flow on the surface. Now, if you look at this equation here, I hope that we can show. Okay, here. This is the equation here. If you look at it here, you see that here you have the resistance. Here is the frequency and the permeability. So the resistance is for copper is usual value, the permeability as well. So the frequency is the only factor here. So when the frequency goes down, the skin depth goes down. So here you see that, skin depth at frequency of 1 gigahertz goes in the range of a few micrometers or even less. Now the problem is that actually, and I will now switch to here, the copper can be rough. So going back maybe, this picture here, the roughness of the copper here at the point when it's attached to the copper laminate, it plays a big role. Now this is quite important because the thing is that I will try to increase this if it works. No, it doesn't. If this roughness is large, then the current would travel longer path. So traveling longer path means that you actually lose more signal because it takes longer path to from a point A to point B, and that's quite annoying. And for highest frequency application, you have to really take care to choose the laminate that has the smoothest possible surface at the point where the copper attaches the laminate. And if you take a normal PCB, the length of the signal that travels could be as much as 3 times longer than the physical distance between 2 points. So the copper roughness can be really different, depends on the type of the PCB, and the effect could be quite large. So the losses at certain frequency could be doubled or halved if you take a better material, which has less roughness. And the best copper layers are rolled layers from the rolled sheets of copper that are attached, are bonded to the surface. The electrodeposited, of course, is the least quality material for that. All right. So this is a summary of printed circuit board materials. So what you should take care about is the copper losses here. So this is FR4, basic FR4. It is a standard foil with some dielectric losses, with some permittivity of 4.2, let's say, spatially changes for 0.2, 0.3 plus minus. And then you can go either, if you want really homogeneous, you have to go to Teflon or even the ceramics or quartz. If you want to have lowest permittivity, you have to go to Teflon. If the epsilon R for the FR4 is 4, then for Teflon it's less than 2. Then to get lower the electric losses, again you can go to Teflons or ceramics. If you want to have lower copper losses, you have to go to rolled annealed copper, and therefore, yeah, the price goes a little goes much higher than you, well, I would say that you want it, yeah, because getting such materials would be also that they would cost maybe 10 or even more times that the normal FR4. Okay, let me finish with the surface finishes. Excuse for the pun. So we have different surface finishes that are actually, I'm not talking about the green stuff here. I'm not talking about this surface finish. I'm talking about these white little islands here, you see. Or not white, the silver pads. So these, let's say, these silver pads, this is what I'm talking. I'm not talking about the purple green coating. So let's go back to the surface finishes. I'm talking about protecting the exposed copper where you solder on. And this copper, of course, you put components and you solder them, and then it is protected. But this surface finish protection is for the time when you produce the PCB and before you actually put the components on. So the most commonly used is so-called hot air solder leveling. Here, the abbreviation is HASL, and you can have with lead or without lead. Of course, 99% of electronics is now without lead, and therefore this would be the most common choice. So HASL without lead. Then you can have silver coating, or you can have immersion tin, electroless nickel immersion gold, or ENIG. This is the second mostly used coating. And then you can have the lowest cost organic solderability preservative, OSP. So what's how you choose, which you choose? Usually if you don't care about shelf life, you go for the OSP. What does it mean? The OSP would last for a few days, maybe a week or two. So the time between you produce the PCB and you assemble it, it's not critical. It's short. And therefore the OSP would serve for its needs, because when you put the components on, you actually burn through this OSP layer, and when you solder them, yeah. But if you want longer shelf lives before the assembly, you go for the HASL. This would go up to, I would say, 6 months. So 6 months is usually the shelf life of the PCBs where you use HASL coating. It's not a problem when you solder manually, because manual soldering could be done anytime. I mean, even after a few years, you can still solder, but it's not that quality anymore. And normally, you have to be in production. You have to be reliable. You have to do it quickly without any repair, and it should last for the whole lifetime. So soldering is quite a delicate process, and any changes on the surface because of the oxidation would make it less reliable, and this would then make your life harder after a few years when the components would start to come back failed. And therefore, if you want to have a longer shelf life, you should go to the gold. And it's not that expensive as someone would think. It's very thin layer. Why it's called electroless nickel immersion gold? Because the nickel layer is between the copper and the gold. Otherwise, gold will just go into the copper and disappear. So how these coatings look like? HSL looks like that. Why is it called hot air solder leveling? Because more or less you apply the solder on top and well, you blow hot air over it to remove the excess of the soft solder. The thing is that maybe it's not that flat as you see here from this picture. It's quite bumpy. It might be a problem in some cases. If you want really flat layer, you should go for gold. Immersion tin, you just take the PCB and you put it in a tin and pull it out. That's it. Immersion silver. Silver is good for contacts usually, for keyboards and stuff like that. But it reacts with sulfur in the air and it may tarnish. So for that, gold is the most, I would say, commonly used for such applications where you need long shelf lives or for some contacts and stuff that should not oxidize in any circumstances. And this is OSB. You see the color of copper in through it. So, more or less, if you go for highest volume and really high speed placing after the components, after the PCBs are made, then you should go for this because it's the cheapest finish you can get. If it's more than few days, then there will be solderability problems already. So it should be really quickly produced. Okay, at the end I would like to show you what you have learned or what you should learn from this lecture. Well, you should list different PCB materials. You should know their main electrical, thermal and mechanical properties and the applications for them. So if I ask you, okay, you should at least know, let's say, what is, that we have FR4, FR1, CEM 1 or 2, then the Teflon, the copper-based or aluminum-based IMS or DBC, and the flexible polyimide and Kapton. You should know what is the approximate dielectric constant. So all of the epoxy-based materials have around between 4 and 5, and that's enough to know. You shouldn't like, okay, 4.73, doesn't make sense. Between 4 and 5, except the Teflon, which has 2. You should know typical dimensions of the PCBs. That's what we discussed earlier. So 35 microns, 1 ounce per square foot, outer layer of copper, inner layer 17, and then the thickness of the laminate 1.6 millimeters, then goes up and down for 1.1 millimeter goes up and down to 100 microns, even less. You should know the material from the picture. If I show you, let's say, if I show you that one, yeah, then you should know, okay, it's a low-end single-sided electronics. It's not transparent. It has this whitish brown color. It is either CEM1 or FR1. Or maybe I can show you, I don't know, this one here. And then you see, okay, it's a high-density electronics. It has some BGAs on it as well, integrated circuits and stuff. And it's probably FR4. But you cannot know for sure, can you? I mean, it could be flexible, but this one is not. So, well. And so on. So you should recognize it from the different points of view. What is the material for the PCB? And you should know what is the most appropriate material for your application. So if I say, okay, what would you take if you want really high heat dissipation and cooling of the components, what would you take? And you should, okay, now, okay, we have DBC or IMS, I would take that one which is the most appropriate or has the lowest or the most suitable thermal conductivity. If I tell you, okay, what would you take for PCB that runs at 10 gigahertz or more, then you would say, okay, Teflon maybe, or even some FR4 which has such a low losses that would be applicable to that. So yeah, there are things you should consider when you go into a certain application. And finally, what do I have? Yeah, some literature. If you want to read more about these topics, there are some books available on EFE, or there are some links shown here. So at the end of each lecture, you would get such a list of literature you can read if you want more information. And that's it from my side. So thank you for your attention. It's already late, and I hope that you learned something about the materials for PCB, and it will be useful for your work later on. See you.